Let's say the quality control manager at Norman, Oklahoma's fourth largest cracker factory suspects that its 10-ounce packages of crackers actually weigh something other than 10 ounces. A random sample of 20 such packages found that the mean weight was 9.955 ounces with a standard deviation of 0.29 ounce. Okay, so we've got a set of hypotheses, and we're just asking a two-tail kind of question. We think, the quality control manager thinks that the mean weight of packages is something other than 10 ounces. Okay, so is the mean 10 ounces or is it something other than 10 ounces? And so we go and collect a sample of size n. Y bar here is 9.955 ounces. And the standard deviation is 0.29 ounces. Okay, and our sample was of size 20. Okay? And so we want to be 95% confident in this result, let's say. So if we were to plot y with this hypothesized mean here, we want to be 95% confident in the result. 0.025 down here, 0.025 here. Okay? What's the probability of type 2 error if the true mean is actually 9.75? Okay, what's the probability of type 2 error if the mean is actually 9.75? Okay, so we're really pulling our sample of size 20 from this green distribution, right? That's really what's going on with the cracker factory. Okay, the mean number of ounces in our packages of crackers is 9.75. What's the probability that we make a type 2 error? That is, what's the probability that we fail to reject the null when the null is false? Clearly, the null is not 10. It's 9.75. So what's the probability that our sample evidence doesn't tell us to reject the null? Okay? Well, that means that our sample mean lies underneath the green distribution, the real distribution. That's where we really pull the sample from, but it lies in the non-rejection region. Okay? Clearly the mean is not 10, but the sample evidence lies in the non-rejection region. Therefore, we didn't reject the null when we really shouldn't have. When we really should have. We didn't reject the null when we really should have. Okay? So we need to find this area. This area is the probability of type 2 error. It's a probability beta. Okay? So we need to find what? These values, these critical values that lie on the y-axis. So we're taking the critical values from the t space and putting them in the y space. Okay? So here is t, degrees of freedom, 20 minus 1. And we want to find these values of t from the t table associated with 0.025 in each tail. Okay? And if we do that, we should find that the value of t is 2.093. So you go down to row 19 over to 0.025, and you should get a value of 2.093. Okay? The symmetric nature of this distribution tells us that value down here is negative 2.093. Okay? So we want to translate these from the t-axis up to the y-axis. That is, this critical value lies 2.093 standard deviations away from 10. Say likewise here on the other side of 10. So let's do that. Here's our y distribution. The mean here is 10. What is this value right here? 0.025 in this tail. And what is this value on this axis with 0.025 in the tail? Okay? Well, this one here, we know this equation. T equals y minus mu naught over s over root n. We know the value t, 2.093. We don't know the value of y. We know the hypothesized mean is 10. We know the standard deviation, 0.29, and we know sample size. Okay? So if we multiply this over, add this over, we should get that the value of y here is 10.14. Okay, so this value on this axis, 10.14. 10.14. Let's find this one. Okay, t is equal to y minus mu 0 over s over root n. We know the value t, negative 2.093. That's equal to the value y minus 10 over s 0.29 over root 20. Okay, that implies that the value of y is 9.86. 9.86. Okay, so actually the mean here, this is 9.86. This mean lies over here. 9.75 actually lies to the left of this value. Okay, this value here, 9.86. So now let's isolate just this green curve. Okay, just the green curve, because that's going to help us give us the area. Okay, so here is just the green curve. Here's y. Here is 9.75. Okay, here's 9.86. It's right there, and here is 10.14. Okay, and the area that we're interested in lies between 9.86 and 10.14. That's the value of beta. Okay, it looks a little bit different here because we didn't know exactly where this critical value is going to lie with respect to this shifted mean, which is mu naught plus delta, which is equal to 9.75. Okay, we didn't know exactly where this was going to be in relation to this critical value, but now we know it's actually over to the left. Okay, this area is the area of the non-rejection region in y space, on the pink curve with mean of 10. Okay, but mean of 10 isn't what is actually going on. We're really pulling our sample from a distribution whose mean is 9.75. Okay, so we need to find this area. How do we do that? We got to convert this now to a t distribution with degrees of freedom 19. Okay, so here's 0, translating 9.75 down, that's 0. And we got to find these two values on this axis down here. So this value of t would be 9.86 minus 9.75 divided by s 0.29 over root 20. As it turns out, that value is 1.69. Okay, this value here, this is 10.14 minus 9.75 divided by s 0.29 over root 20. That value is 6.01. Okay, and this area in between these two values is beta. So one way to think about this now is that beta is equal to the probability that lies between a t value of, a t is degrees of freedom 19, between 1.69 and 6.01. Okay? So we can go find this stuff from the t table. Okay? As it turns out, the area above, let's see, the area above 4 degrees of freedom 19, the area above 1.328 is 0.1. And the area above 1.729, that area is 0.05. Okay? 1.69 lies between 1.328 and 1.729. So that must mean the area in the tail above 1.69 must be between these two areas. Okay? So the area in the tail above 1.69, this area in the tail, mind you, is between, let's see, let's call it area. That area is between 0.05 and 0.1. Okay? We don't know exactly what it is because we don't have that exact value, but we know it's between 0.05 and 0.1. Okay? What's the area above 6.01? Okay? As it turns out, that's really big. whenever we have degrees of freedom 19. Okay, that the area above the tail associated with 6.01 on the axis is essentially 0. Okay, there is no area for our purposes above 6.01. This area right here, tiny. That's six standard deviations away from the mean. Okay, very tiny area, negligible. That probability is 0. So this area above 1.69 is actually our beta. That area is beta. Beta lies between 0.05 and 0.1. Okay? What's the probability of type 2 error when the true population mean is 9.75? That probability lies between 0.05 and 0.1. It's a very small probability. And why is that? We have a very small standard deviation and a somewhat large sample size. So whenever you divide 0.29 whenever you divide 0.29 by the square root of 20, you get a very small standard deviation. Okay, so that makes the difference between 10 and 9.75 stand out all the more. Okay, we'll probably really be able to detect the difference between a mu naught of 10 and a mu naught of 9.75. We're probably not going to fail to reject the null whenever the difference is this great, when the standard deviation is this small. Okay? This is a very small probability of type 2 error. It's a very small probability that we fail to reject the null when the mean is really 9.75. Okay? We could also use Excel. If we don't like bounding this thing, we could use Excel here. That is the t-dis function. If we read in this value, 1.69, 4 degrees of freedom 19, and we just want this upper tail, one upper tail, okay? That value is 0.054. 0.054. This is beta. That's the actual value of beta, 0.054. Okay, so it's somewhere in between these. If you actually calculate it out using Excel, you get 0.054. Okay? Another way to say that is only 5% of samples will tell us to not reject the null when the mean is really 9.75. Okay, it's not going to happen very often. This is a very small probability of type 2 error.